Okay, let's talk about radioactive decay. Radioactive decay is always first order. So, we now know, because it's first order, that the integrated rate law is this, that the natural log of the concentration of A is equal to minus kT plus the natural log of my original concentration. But when we talk about radioactivity, a lot of times, since they're solids, then my concentrations, we can also just use the amount of A, could be in mass, or it could also be in terms of its radioactive count, because the radioactive count is relative, directly relative to the mass. So we can use that as well. So A could be the mass, it could be the radioactive count. So how much radioactivity is being emitted. The other aspect is this. Not only do we have our integrated rate law, but we also have our half-life. And the half-life, remember, is equal to the natural log of 2 divided by the rate of decay. Okay? Finally, if we look at the half-life, it's not dependent upon my initial concentration of radioactive material. And what we say is for every half-life, we have half the amount. The definition of a half-life is that at time t1 half, you have half the amount of your initial concentration. What does that mean for us? Let's take the situation of strontium-90. Strontium-90 has a half-life of 28.8 years. Strontium-90 is a byproduct or a product from basically our nuclear reactors. Even though the half-life itself is short, it is one of the more potentially dangerous radioisotopes. It's called bone seeker. It basically, if it gets ingested, it will replace our calcium. And in the internal organs, what results from that is that you have radioactive material that's lodged basically in all your bones and is a source of bone cancer and the cancers of organs that are near your bone marrow. All right, so let's do an example of radioactive decay. If I have 8 grams of strontium-90, how much remains? After 4 half-lives. Now remember the graph. If we look at this, if this is my initial amount, then at T1 half, you can have half that amount. So this is A naught. Okay? At T1 half, further out, it's going to be half of this amount. At T1 half here, it'll be here, and T1 half there, it'll be down here. So your graph is very slow decay like this. At each of these points, this will be 1/2 A naught, half of a half A naught is 1/4 A naught. Half of this would be 1/2 cubed A naught, so 1/8 of A naught. And this one is going to be 1/16 A naught. So, knowing that, we can say that 1A is equal to 1/2, 4 half-lives out, times 8 grams, because that's my A naught. What we get is 0.5 grams, okay, of strontium-90 that remains. Okay, so that's one way to do the radioactivity based on just the half-lives. What happens if you don't have such an even number, like I don't have exactly 4 half-lives out? Well, what else can you do? So, let's try this example. Carbon-11 has a half-life of 20.4 minutes. Okay? So essentially, what percentage remains after 5 half-lives? So if we know that A is equal to 1/2 to the 5th A naught, then the percentage A over A naught is going to be equal 1/2 to the 5th. So 1 over that should be 32. 32. And so the percentage will be equal to 0.03125 times 100%. So the percent remaining is 3.13%. Okay, so that's just using the property that radioactivity has a first order decay. What about dating? Well, radiometric dating. If we use carbon-14, it's called radiocarbon dating. Okay, so how does this work? So just so you know, radiocarbon, carbon-14, undergoes what kind of decay? What kind of decay is this? It's the beta decay. Okay, and the half-life is basically 5,700 years. This is 2 sig figs, 2 significant figures. All right, so if we wanted to determine the age of a piece of wood, okay, in this case, we're going to use its radioactivity as a determination of the amount of material there. So let's say that they have measured 11.6 disintegrations per second. okay? And fresh wood, okay, has been shown to have 15.2 disintegrations per second. So what is the age of the piece of wood? All right, so let me erase this and we'll go through and determine that. We know natural log of A is equal to minus KT plus the log of A naught. A we're going to use as 15, A naught we're going to use as 15.2 disintegrations per second. A, we said, was 11.6 disintegrations per second. K is equal to we don't know, is equal to the natural log of 2 divided by t 1/2. And t 1/2 is equal to 5,700 years. Okay, this formula basically comes from t 1/2. There's the half-lives. The half-life for a first order reaction is natural log of 2 over k. Okay, so now what we'll do is we'll go ahead and rewrite it to solve for k. So the natural log of A over A naught, okay, is equal to minus kt. We're going to solve for t. So t is going to be equal to minus 1 over k times the natural log of A over A naught. So now that we have our equation, we'll just go ahead and fill it in. Minus 1 over k is equal to log of 2, so that's 0.693 divided by 5,700 years times the natural log of 11.6 over 15.2. And so we get, for t, it's going to be basically 11.6 divided by 15.2. Let's take the natural log of that, okay, times 5,700 divided by 0.693. So we get 2,223 years old. This piece of wood is 2,223 years old. Since we're talking about two significant figures, 2.2 times 10 to the third years. Okay, so this is the age of the wood object. All right, so let's do one more example before we move on. So another example would be this one. Suppose we had a piece of rock, okay? And if we look at the rock, what we find is this ratio, that for every 1 milligram of uranium-238 in this rock, you have 0.257 milligrams of lead-206. And the basic hypothesis behind the presence of lead-206 is that it's believed that all of the lead-206 on Earth actually comes from the radioactivity of uranium-238 as it goes to its radioactive decay chain and it forms the lead-206. If that's true, then basically we know this is A. So then the next part is we need to find out what is A naught, and we need our half-life, the half-life of uranium-238, which we will need, is going to be equal to 4.5 times 10 to the 9th years. Okay, so let's find A naught. If I have 0.257 milligrams of 206, lead-206, then we need to find the moles of lead-206. And we know that the mass is 206 grams of lead-206 for every 1 mole of lead-206. Okay? The reason I keep repeating this is because that mass is specific to this isotope. We know it's a 1-to-1 ratio between uranium-238 and lead-206, based on the previous discussion of our decay chain. Okay, and we know that the mass is 238 grams of uranium-238 divided by 1 mole of uranium-238. Okay, and what does that give us? What that gives us is from 0.257 milligrams of lead, it came from 0.259 milligrams of uranium-238. So now we know that A naught, the original sample, currently contains 1 milligram. Should be 2 sig figs of 238 plus what had been converted, which is the 0.259 milligrams of uranium-238. So now we know what A naught is. Okay? So once we find out what A naught is, we can go through and use our formula to determine the life of the age of this rock. So we know we're going to use this equation, A over A naught, natural log of A over A naught, minus KT. And we know that K is going to be equal to the natural log of 2 divided by T 1/2. So if I plug that in, I have 1 milligram divided by the 1.259 milligrams. So this is all my uranium-238. So A over A naught is equal to, and K is equal to 0.693 divided by 4.5 times 10 to the 9th years. That's how long it takes for my half-life, times T, which is going to be the age of my rock. So T, I'm going to calculate this out, ends up being 1.7 times 10, let me see my sign there, 10 to the 9th years. So that's how you figure out the age from radiometric dating of any object, even if it's not a specific whole number of half-lives. Now before I continue on to the next topic, let's talk about A and A naught. So normally when we talked about using our first order rate reaction, the integrated rate law, we use the concentration of A and the concentration of A naught. But since we're talking about solids typically for radioactivity, since the volume that concentration is the same. So we can just use the mass. But another thing that's directly related is radioactivity. So what are the units for radioactivity? So the SI unit for radioactivity is the becquerel. And what this is, it's 1 disintegration per second. And instead of using becquerels when we were doing the carbon-14 radiometric dating of a wood object, we spelled this out. That's basically, it was the number of becquerels that you see. There's another unit, that's what they use, it's called a curie, after Madame Curie. Abbreviation is CI. And this is basically the decay of 1 gram of radium. When you undergo that decay, it's 3.7 times 10 to the 10th becquerels. Okay, so you can convert between curies and becquerels. Most often, curies are very large, so we often talk about radioactivity in terms of millicuries. Okay, and that's it for doing radioactive decay.